guys, welcome to the last exercise, last group of experiments for the microbiology lab. So today we'll be learning about the spectrophotometer. So spectrophotometer is a device used to track the growth of the bacteria. Today we'll be monitoring the growth of E. coli bacteria. E. coli is a gram-negative bacteria which has a very less generation time. So in other words, it grows pretty fast, and that's the reason majority of the lab experiments we do with E. coli. So it's a very good model microorganism, and we have picked E. coli today to demonstrate how you can use the spectrophotometer to track the growth of the bacteria. So why do you need to track the growth of the bacteria? A patient comes in with an infection, you take the sample from the patient. The first step is to grow the bacteria. If you're able to grow the bacteria, you can do all the diagnostic tests and identify the organism. Okay, so that's the reason it's very important to learn how you can track the growth of the bacteria. So how do you know if the bacterial cells are actively growing or not? You take the sterile media. So sterile media would be something similar to this. This is sterile LB broth. Similar to your tryptic soy agar, this is another bacterial media, food for the bacteria, that is commonly used in labs to grow different bacterial cells. Today we are using LB broth, Luria Bertoni broth, and we inoculated, or we started the culture of E. coli in the sterile media. Then this flask was incubated for approximately 4 to 5 hours. You can see the difference between the sterile media versus the media that has a lot of bacteria in it. So after 4 to 5 hours, you grow the bacteria at 37 degrees using constant shaking. So the shaking would make sure oxygen is very nicely distributed to the bacterial cells. The bacterial cells will reproduce, they will double up every 20 minutes, and you can see that the cells become cloudy. Through these 4 to 5 hours, every 60 minutes, we can always collect the samples from the bacteria and track the growth of the bacteria. So how do you track the growth of the bacteria? We use a spectrophotometer. Spectrophotometer is a machine that uses the source of light and absorbance of those light molecules by the bacteria are an indication of the bacterial growth. Okay? So you have the spectrophotometer here, and I'm going to demo you how to use this machine. It's a very small, simple instrument. You can set the wavelength of the visible light or any other light if you want to use. You can set the wavelength using the circular knob that is right here. And for the bacteria, we know that the bacterial cells, they absorb the most at the visible range, which is 600 nanometers. So I set the wavelength to 600 nanometers, and you have this opening here. This is known as a cuvette holder. So cuvettes are special glass tubes that are designed to absorb the light efficiently, and they are designed specially for the spectrophotometers. So this is a glass cuvette, and this can fit right into the cuvette holder like this. Okay, so any instrument, before you begin your analysis, we need to blank the instrument. So blanking makes sure that you are actually taking care of any background noise or the background readings that you get from the other liquids that you use. Because we are growing bacteria in a media, for us the blanking should be with the plain media. Okay, so I'm going to take some sterile media and then blank the instrument. Okay, so open your sterile media, and then you have your, this is the pipette gun, and approximately take 9 to 10 milliliters, and make sure you release it into the cuvette. So I'm going to just put it to the side before I take the readings. I would like to show you a few things about the spectrophotometer. So you have two modes in the spectrophotometer. A mode that is highlighted right now is A, which stands for absorbance. If you are measuring the absorbance or the amount of light that is being absorbed, you would go in this mode, A. If you want to measure the light that's transmitted, that's not absorbed but that's transmitted, you would go with the mode T. But usually we always go with the absorbance mode. So right now this is at absorbance mode, and all you need to do is put the cuvette with the media and hit this button right here. So that button would make sure you're blanking the machine, you're negating any background noise that you get from the media. Okay, so this is the blank cuvette. All you need to do is put the blank cuvette all the way inside. And before, oh, I forgot to mention something. So before you put the cuvette inside, always make sure you're wiping the surface so there are no oils or any other marks from your gloves, because that would interfere with the absorbance. So make sure you clean the cuvette and press this gently and close the cuvette holder. And now you need to hit this button that's right next to the mode button. So it says BLA, so we understand that the machine is blanking, and don't touch it, it's blinking. Once the reading stabilizes to 0, you're all good to go. See, you can see that the readings are at 0.000, so that's blanking is all done. I'm going to open the cuvette holder and gently remove the blank cuvette. So once you blank the machine, you're good to take multiple absorbance readings. You don't need to blank at every sample absorbance readings. Okay, so you're good if you blank once. Now I do have two cuvettes. One cuvette is taken, this has a sample for the 60-minute growth of the bacteria. So I grew the bacteria for approximately an hour and I took the sample, so we can track the growth of the bacteria over the time. So you can have the first time point at 60 minutes, the second time point at 2 hours, and the third time point at 4 hours, so on and so forth. So this would make sure your bacteria is growing actively. So the absorbance values have to increase. Okay, so this is going to be your 60-minute reading, and let's take a quick look at the absorbance. So all you do is just wait to see the absorbance. As you can see, the reading is pretty low because the bacteria is still in the lag phase. The bacteria would take a long time to stabilize, they would adjust to the new surroundings, and then after, depending on how fast they are picking up, maybe after 2 hours, the absorbance would double up. Okay, so this is still at 0.05 because the bacteria is still in the lag phase. I have 2 more readings that would show you how the bacteria is actively starting to grow. Okay, I have the sample after approximately 2 hours. So the bacteria has been growing for 2 hours, and let's take a quick look at the readings. Okay, there you go. You see that the absorbance readings increased from 0.05 to 0.282. So the bacteria is potentially going into the exponential phase. Then you take a note of the reading, remove the cuvette, and I also have the sample that has been growing for almost 4 to 5 hours. I can see it's pretty cloudy, so this is at the peak of the exponential stage. There you go. So you have the absorbance readings at 1.48, and after this point where the readings reach a peak, they stabilize over the time, so they reach the stationary phase, and that's when you have to stop the culture, because if you continue growing the bacteria, they would go to the stationary phase, and then because of the nutrient consumption, the cells would go into the decline phase. They start like dying and they start releasing toxins. You don't want that for all your experiments. Whenever you're planning your microbiology diagnostic experiments, you want the bacterial cultures to be in the late exponential phase or early stationary phase. So that's when you can do all your diagnostic tests. So this absorbance value represents that the bacteria is at a very good growth stage, and you can stop the growth of the bacteria, do your diagnostic tests. Okay, so this is about the spectrophotometer. But before we complete this exercise, I just have a quick question for all of you guys. Though we are tracking the growth of the bacteria using the spectrophotometer, we also need to make sure that the cells are actively reproducing and growing. Why do you think we need to do that? All right, I'm just going to pause for a quick 10 seconds and give you the answer. So in other words, my question is, we are tracking the growth of the bacteria using the spectrophotometer, but still it's very important to grow the bacterial cells on the TSA plates and observe the growth on the TSA plates also. Even if you see an increase in the absorbance, it's really important to grow them on the solid plates and see that they are actually growing. Why? Yes, the answer is, I don't know if any of you got the answer. The reason we do both is the absorbance simply comes from the cloudiness. So the cloudiness sometimes can also be from the dying cells. If the cells are dying, they release a lot of these cell debris, and that cell debris can also give you an absorbance value. So that absorbance won't actually represent the cells, bacterial cells really growing, but actually it's the cell debris. So just to make sure you're not missing out on any of those dying cells, you grow the bacterial cells on the solid plate. When the bacteria can actively reproduce and grow, you're 100% sure that those bacterial cells are alive. Viability of the cells is always best studied when you grow them on the bacterial plates, not just simply by looking at their absorbance values. Okay, so that's the reason we always make sure you track the bacterial growth on these petri dishes. So I have this actively growing bacterial sample, and I'm going to show you how to track the bacterial growth on the petri dish. So once you have the actively growing bacteria, just to make sure the cells are viable, we spread them on a TSA plate. So I'm taking some of the sample, approximately 100 to 200 microliters, and add on the petri dish that has the tryptic soy agar media. So I'm just going to spread them or add them as tiny dots. So this is all the liquid I have on the petri dish. For you to be able to see the bacteria growing as single colonies or as a lawn, we need to really make sure the bacteria is sticking onto the surface. And how do we do it? We use these L spreaders. Now there are many names for this tool. This is known as a hockey stick. This is known as an L spreader. You can call it address it any way you want. So you have this liquid sitting right on the TSA plate, and all you need to make sure is you're nicely rotating the plate so that all the liquid that is right there is absorbed. The cells go inside so they can get the food and they can grow and give you visible colonies or visible lawn. So you do this action until and unless you feel the friction, so all the liquid is absorbed onto the TSA plate. I don't know if you can see this clearly, but all the liquid is taken inside, it's absorbed, and I can feel the friction now. So this is good to go, and this is spreading. So you label the plate, you label the plate with the name of the bacteria, with your name, and then incubate upside down at 37 degrees and check for the growth after 24 to 48 hours. So this is how you can definitely confirm that your bacteria, whatever you're growing, whether it is E. coli or any unknown bacteria, is viable. Only if you see growth on the plate, they are viable. Simply by looking at the absorbance, you cannot judge whether the bacteria is alive or not. Okay? All right, so we are done with the first exercise. So all we need to learn in this lab 5 is about a very important technique that's known as Kirby-Bauer disk diffusion method. So Kirby-Bauer disk diffusion method is the standard method that is used by many diagnostic laboratories to check the antibiotic susceptibility or resistance of a microorganism. So for example, a patient comes with an infection, you take the sample, you collect the sample, you grow the bacteria, but then you don't know what antibiotic to give. Yes, of course, we have many broad spectrum antibiotics, but then you have to really make sure that those antibiotics actually be able to work on the bacteria that the patient has and be able to control that infection. So for that, commonly used method is the Kirby-Bauer disk diffusion method. This little tool that you are seeing here is the antibiotic dispenser. Okay? So you have 1, 2, 3, 4, 5, 6. There are 6 antibiotics, which are different antibiotics. Some are cell wall inhibitors, some are cell membrane inhibitors, some are bacteria protein synthesis inhibitors. So some are narrow spectrum, some are broad spectrum. So you can test whatever antibiotics that you want to. And simply, you grow the bacteria on the TSA plate, you punch this antibiotic dispenser on the plate, and then this antibiotic dispenser would release the so-called filter discs. The filter discs are right on that side. Let me just separate them and show you. This is how the different filter discs look. There are the 2-letter codes on them, which would indicate the name of the antibiotic. For example, you have, tetracycline, TE, and you also have ciprofloxacin, CIP, and there is also a number below the font that indicates the concentration of the antibiotic. Okay? So those filter discs are all right inside these little things that are inside the antibiotic dispenser. Okay? For the demo purposes, I am going to show you Pseudomonas aeruginosa bacteria. So the first step is to spread the bacteria on the TSA plate and then dispense these antibiotics. Why do you think I chose Pseudomonas aeruginosa? Pseudomonas aeruginosa, Staph aureus, and then E. coli and Enterococcus facilis. All these 4 different bacteria are very popular to cause so many nosocomial infections, the hospital acquired infections. Especially Pseudomonas aeruginosa is resistant to many antibiotic treatments. People who have cystic fibrosis patients, and people who have these burn wound infections, all of these people, they commonly have these Pseudomonas infections because it's resistant to so many antibiotics, and it's a big challenge for the physicians to come up with the right antibiotic to treat the patients. In that sense, Pseudomonas is interesting for us because we can see, I'm going to grow the bacteria and then show you the results, upload the results in few days, so you would understand how resistant Pseudomonas is to different antibiotics. Okay, so the first step is to grow the bacteria, for which I need a sterile swab. And before I do anything, I need to just label it. So you have the name of the bacteria and your initials, or your name written and the date. Open up the swab, pick the bacteria, and swab every corner of the TSA plate. Because you want your bacteria to grow really well, so when you add the antibiotics, you can see for zone of clearance. Right. Open the lid. Make sure the dispenser sits right on the plate and press it once. There you go. So you can clearly see there are 6 different antibiotics, and those antibiotics are on those filter discs, and that antibiotic would diffuse. So that's a reason the name of the technique is Kirby-Bauer disc diffusion method. The antibiotics would diffuse into the media, and when the bacteria would grow in 24 to 48 hours, those antibiotics would start acting on the bacteria. So if the bacteria is resistant, it won't care, it would still grow. If the bacteria is sensitive to that specific antibiotic, what's going to happen is you're going to get zone of clearance. You have the TSA plate and you added the Pseudomonas bacteria, you heavily swabbed it. After 24 to 48 hours, you will see visible growth as a lawn of bacteria. Then what happens is, as the antibiotic dispenses or diffuses into the media, it would start killing the bacterial cells around it. So when you come back in 24 to 48 hours, you expect to see something that's known as zone of inhibition or zone of clearance. So you'll not see bacteria around the antibiotics if the bacteria are sensitive to that antibiotic. If the bacteria are resistant to the antibiotic, you won't see any zone of clearance. They don't care. They just keep growing around the antibiotic. Okay? For example, antibiotic 6, if it is very efficient, you will see a very big zone of clearance. So the bigger the zone of clearance is, the better the antibiotic would work against that bacteria. Okay? So you would want to prescribe that antibiotic that the patient is not resistant to. Patient's bacterial sample is not resistant to. Okay? I'm going to also tell you about a quick interesting fact. Sometimes, though you see the zones of clearance, you might see small colonies around that zone of clearance. Those small colonies that grow around the zone of inhibition are known as satellite colonies. Satellite colonies. Can you think what these satellite colonies could be? So the tiny bacterial colonies that are growing inside the zone of clearance, they are the resistant colonies. The bacteria probably is not resistant, but it is sensitive to the specific antibiotic, but there are some colonies or some of the bacterial cells that would develop resistant to that antibiotic. So those are known as satellite colonies. They can be because of some mutations, random mutations can happen, and sometimes bacteria, when it undergoes a lot of stress, all of a sudden, it becomes resistant to the antibiotic. Okay? When you see there are satellite colonies, you would want to avoid that antibiotic. Okay? But if you don't have any choice, if the patient is allergic to all other antibiotics and this is the only choice, then you can go with that antibiotic. Okay? So those are satellite colonies, and this is the Kirby-Bauer disc diffusion method. I'm also going to upload a document that would help you read the results of the Kirby-Bauer disc diffusion method. So what you need to do is you would measure the diameter. Say for example, you have, this is the zone of clearance, the circular area around the antibiotic 1. You would use a ruler, you would measure the diameter in millimeters, and then Depending on the diameter, you would decide whether that specific antibiotic is working against that bacteria or not. If you have a very, very small diameter, then probably that's not a good antibiotic for that bacteria. If the diameter is very low or very small in number, you would want to avoid that antibiotic. So there are certain things that really help you, come up with the specific or the good antibiotic for the different patient samples. I'm going to upload that document on Canvas so you can easily understand how these herpes-bower BIS diffusion results are read in real case scenarios. Okay? Thank you.